Good morning, everyone. So there are many possible ways by which fires may impact the climate system. As Professor Harvey mentioned in the first talk, when peat is drained, it can release enormous amounts of carbon dioxide, especially when it's burned. So last year, during September and October, on certain days, it's estimated that the carbon emissions from fires in this region exceeded the entire carbon dioxide emissions of the entire US economy. In addition to emitting carbon dioxide and other greenhouse gases, these fires also emit many other compounds contributing to the haze that we're also familiar with. Of particular importance are organic carbon aerosols, small particles suspended in the atmosphere. So this photo shows a layer of haze. Looking down at it from an aircraft flying above the haze layer, you can see that the haze looks milky grey, almost white from above. And that's because the organic carbon aerosol particles and other aerosol particles are scattering lots of the incoming sunlight. So this means less sunlight reaches the Earth's surface, and the Earth's climate system is cooled as a result. And it's also possible that these aerosol particles may impact the clouds. So one theory suggests that as we add more aerosol to the atmosphere, that can mean that cloud droplets increase in number, making the clouds whiter, again scattering more sunlight away from the Earth's surface and cooling the climate system. And it's also possible that the aerosol particles may affect cloud cover and rainfall, although the uncertainties are large. In this study, we've been looking at the climate impacts of the organic carbon and other aerosols from fire emissions, and we've used a global climate model to look at this. Of particular importance is the representation of the aerosol effects on the clouds. Most climate modelling studies assume that emissions from fires are invariant, so they don't take into account interannual variability. However, in reality, variability in fires leads to variability in the emissions. So this shows organic carbon emissions globally, the aerosol emissions from 1997 through to 2006. The yellow shows emissions from non-fire sources, such as residential fuel use and industry. The blue shows emissions from grass fires, while the red shows emissions from forest fires. Peat fires are included in the forest fire category here. And you can see that interannual variability in the fires leads to the interannual variability in these organic carbon aerosol emissions. We've run 10 simulations for each of these 10 different years. And we've also run an 11th simulation, just taking the mean emissions. So this simulation, F-mean, represents the conventional approach of ignoring interannual variability and using interannually invariant emissions. And we've also run a reference scenario, F0, which has no emissions of aerosols from fires. So this represents the conventional approach used in most climate modelling studies. So F-mean represents the conventional approach. F0 represents the control, where you don't have the emissions from the fires. And these are some of the results that we find for the global mean radiative impact of the aerosol emissions from the fires. So the values are negative here, and that's showing that the aerosols are having a cooling impact on the climate system. And that is primarily due to the impacts of the organic carbon aerosol on the clouds. The interannual variability is large. If we average across these 10 simulations for the different years, we find a mean value of roughly -1 watt per meter squared, which is roughly about half as strong as the warming impact due to carbon dioxide and other greenhouse gases emitted as a result of human activities. If we look at the simulation using the mean emissions, F-mean, we find that the strength of that cooling effect is overestimated by about 23%. So this shows that the conventional approach of ignoring interannual variability can overestimate the strength of the cooling effect. And this is likely due to the non-linear influence of the aerosol particles on the clouds. If we look regionally, for example, in this region, the Western Maritime Continent, we can see similar things are happening. So the aerosols are having a cooling effect, lots of interannual variability, particularly in 1997, which was a really bad burning year. And if we use just the mean emissions, we can overestimate the strength of the radiative effect by almost 50%. So the two main conclusions to take away are firstly that the aerosol emissions from fires can exert quite a strong cooling effect on the climate system, especially regionally, although the uncertainties are large. And secondly, that if we ignore interannual variability, we may overestimate the strength of that cooling effect. Although we've looked at the radiative effects here, it's possible that this might also have implications for rainfall, which is something we've also been looking at. So thank you for listening, and does anyone have any questions? Yes.
What do you think the effects of rainfall are? Do you think there's a feedback to Mars? What are your thoughts on that?
Okay, so the question is, what are the possible effects on the rainfall and whether that may feed back on the fires? So there's two timescales we need to consider when we look at the impacts on the rainfall. There is the fast timescale, where we just look at what happens to the rainfall whilst keeping the sea surface temperatures all the same. And we find here that these emissions do seem to suppress rainfall near the emission sources, but we haven't yet looked at the longer timescales, and the effect would probably be stronger then, because if you are cooling the climate system, you cool the ocean, and so there's less evaporation. So it's possible that this may have a feedback on the fires. If we're suppressing the rainfall, it may make it easier to burn. But there's still a very large human factor draining the peat swamps, potentially starting fires, that we also need to consider. Does that answer the question? Yeah.
So I'm curious what the assumptions are about sort of vertical transport of the haze are. It looked like it was getting quite from your aircraft photograph. It gets pretty high in the atmosphere. Kind of my anecdotal experience from the West Coast, fires out there tend to sort of peak out sort of at lower altitudes. So what carries this so high into the atmosphere?
Okay, so our model does take into account the three-dimensional motions of the atmospheric system. So it is possible for the haze to be transported higher. But the assumptions about the emission height do make quite a large difference to how high it gets. So those assumptions vary depending on the region and the type of the fire. So generally in this region, because the temperatures aren't very high for the fire, it doesn't rise that high. But then if you have a very large forest fire in the middle of Siberia, for example, the smoke plume can get very high. Yes, does that answer the question? Yeah, okay.
Thank you very much.
Thanks.